Hello friends, welcome to my channel. Let's have a look at problem 2464, minimum subarrays in a valid split. In this video, we're going to share some solution formats based on dynamic programming. So here we are going to share two formats. First, I'll read through the problem statement to digest the requirement, and then we do the analysis, and finally we share the code. First, let's look at the problem statement. So given an integer array called nums, so we want to do a split for this array, and we want to find the minimal number of subarrays in a valid splitting. So a valid splitting actually consists of the following two parts. First, so the GCD of the first and last elements of each subarray is greater than 1. So the second requirement is that each element of nums belongs to exactly one subarray. So in other words, the subarrays form a partition of the original array. So here are three examples. So in this problem, the number 1 is very special because if we compute the GCD of 1 with some other integers, so we're going to get 1. So for example, in example 3, so the return is -1. In other words, there's no valid split. So in example 2, so we can have two subarrays for a minimal valid split. The reason is each single element is not 1 here, right? So the GCD is itself, so we get 2 for this example 2. And for example 1, actually here the problem explanation lists one valid split which has two subarrays, so given by 2, 6, and 3, 4, 3. So actually, if we use our intuition, right, so the first integer is 2, so we want to start from the very right. So we have 3 and 2 have common GCD, that is 1, so we cannot use 3, so we can use 4, right? So we have 2, 6, 3, 4. So this is the one subarray, and the other is 3. So in other words, 2, 6, 3, 4. And this is the one subarray, and 3 itself is another subarray. So these two subarrays also form a valid partition. So the minimum number of the maximal number of subarray for minimal splitting is 2, right? We still return 2. So before we look at the analysis, let's look at the problem constraint. First, the nums is not empty and its length is bounded by 1000. So the elements in the list is not negative, and it's bounded above by 10 to the power 5. So with that said, we are ready to look at the code. So actually the code is very self-explaining. So let's do this first for our version 1. So I'm going to define or interpret DPI, the minimum number of subarrays in a valid subarray splitting for the subarray from the very beginning and ending at index I. So in other words, for nums, semicolon, and I+1. So here I'm going to call n the length of this nums array. So next we want to explain the dp update rule, right? So this is the core part. So here I'm going to use this initialization. So float infinity. And float infinity means that a array cannot be do not have a valid split according to the problem requirement. So here actually we can first determine the dp0. It corresponds to a list containing a single number, that is num0. So if this element is not 1, so dp0 will be 1, right? So in other words, there is a valid splitting and the number of subarrays is 1 for sure. Then for the generic case, so if nums_i equals 1, so we do not need to update because there's no valid n split ending at I in this case. So if nums_i does not equal to 1, so we're going to do the update as below. So in other words, what we want to see if we can pin or append this element from the previous ones in the from the middle point up to this index I from some middle point g. So here first, if j equals 0, right? And then we are just need to check if nums_i and nums_g also equals 1. So if this is the case, so dpi should be 1. So this is the this case can be absorbed to the generic case. So otherwise, so we can consider all the possibilities of middle points up to this index I. So if dpj minus 1 does not equals to float infinity, it means that there is a valid split from the very beginning and ending at g minus 1. And then we want to check if nums g and nums I, so this is the end of the new list starting from index I and ending at index, starting from index g and ending at index I. So if their GCD is greater than 1, so from 0 to index 1, g minus 1, we can have a valid split. And then from index g ending at index I, so it's another valid subarray. So in this case, we're going to update dpi to be the minimal of its previous state and dpg minus 1. So this is the number of subarrays for a best or optimal split for 0 up to index g minus 1. Then we add this 1. So this 1 corresponds to the subarray starting from index g and ending at index I. So afterwards, we just need to return dp negative 1 or dpa minus 1. So this is the first version of dp we want to present. So now let's look at the code. So actually the above code is almost the solution exactly. So now let's write it. So first I'm going to introduce this n. So this is the length of this list. And then we're going to do dp initialization. So this float infinity and times n, right? We can do this because this float is a immutable object. And then we are going to do the dp update. So we want to set dpi. So for I in range m. Then we are going to absorb this case in the general logic. Then for j in range, so the middle point can be any from 0, 1 up to I, right? So let's say I plus 1 here. And then what we are going to do is to check if j equals 0, so the first element, right? Then we just need to see if math GCD nums I, nums g, and nums I. So at the very beginning, when I equals 1 and when I equals 0, g equals 0. So GCD of a number itself will be itself. So we are checking if that number is 1 or not, right? That's this case here. So if nums g, nums I, so it's greater than 1. So we're going to set dpi to be 1. So this is one case. Another case is for g greater than 0. In this case, we can consider dpg minus 1. So dpg minus 1. So if we want to consider if the subarray from index g ending at index I is valid, we want to check the state for dpg minus 1. If this does not equal to float infinity, it means that we can have a valid split from the very beginning up to index g minus 1. And then we want to check if nums g and nums I. So these two numbers are the two ends for the subarray starting from index g and ending at index I. So if this GCD is greater than 1, then we can update dp. So dpi will be the minimal of the previous state. And then, so if we use g as a start point to include I, so what's the number of subarrays? So that is j minus 1 plus 1. So the 1 represents the subarray starting from index g and ending at index I. So once we check all the possibilities, so we actually get the best number of subarrays if there is a valid split for ending at each index. So what we are going to return is nothing but dp minus 1 or dp negative 1. So this is actually a solution format for this problem. So we can first do a check. Yeah, it passes the special case. So now we can actually print out this dp table to have a better feeling. So for this, yeah, so this is a dp table. So I'm going to comment out this one and check for generic case. Yeah, so here the return is some problematic. So dp -1 if dp -1 does not equal to float infinity. So otherwise we're going to return -1. So let's try again. Yeah, it passes all the cases. So this is one solution format for this problem. So now I'm going to copy this function signature and share another solution format. So I'm going to change this one to be solution v1, and now I'm going to use this one as v2. So we're going to use cache, and we do not use tabulation. So we're going to use cache dp. So for this, so let me delete all of this. So first I'm going to use cache this decorator. So I'm going to define dpi. So this is the function, right? So here the dpi, we're going to return the minimum number of subarrays in valid splittings, right? So this is for nums. So I'm going to, starting from I and up to the end, right? We are going to write from the back end to the front end. So for this, first I'm going to check if I equals n. In other words, the index auto bound. So we're going to return 0. So this is our stop condition or base case. And then we're going to introduce the float infinity. So essentially the same solution as above. And then what we're going to do, so here we check all the possible middle points. So for g in range, so I, so this I can be included, so up to m. Then what I'm going to do is that, so we're going to check if math, so gcd, so nums I and nums g. So if this equals 1, so we just continue, right? Otherwise, so what we're going to do, we're going to update this result to be the minimum of the previous result state, and then plus dp and g plus 1. So in other words, we want to consider, so this 1 now represents all nums, so starting from index I and ending at index g, so in other words g plus 1 here, right? So that's the interpretation. So finally, once we finish this loop, so we're going to return the result. So this is our main function. So what we are going to return is actually nothing but result. So if, so here I'm going to define this result as dp 0. So we can do this after since Python 3.8. So if this guy, so if we introduce the variable is less than float infinity, in other words, does not equals to float infinity. Otherwise, so we're going to return -1. So this actually you can compare the two solution formats. Essentially, they're the same but different representation formats. So let's do a check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases. So this time we didn't make the mistake that we directly return the result without considering the case that there's no valid split. So here in this video, we shared two solution formats based on DP. So one is using tabulation, so one without. So essentially these two are the same, right? With slightly different interpretations. I guess this one is sort of more straightforward. So with that said, I guess that's about it for this video. Thank you.